Have you ever stopped and wondered how we draw the lines that define our world? You know, from the little plot of land your house is on, to the path of a highway, all the way up to the actual map of your country? Well, there's a hidden science behind all of it, a whole system of measurement and geometry that shapes literally everything. Today, we're going to pull back the curtain on the science of surveying.
Okay, let's just jump right in with a puzzle. Take a look at this piece of land. It's not a nice, neat square or a perfect circle, is it? Nope, its boundaries are all irregular, they're curved, they're complex. So how in the world would you even begin to figure out its exact area?
And right there, that's the fundamental challenge that surveyors face every single day. The real world just doesn't come in simple geometric packages. Yeah, those formulas you learned in high school for squares and triangles, they're not going to cut it when you're dealing with a winding riverbank or a hilly field.
So the solution is actually pretty brilliant in its simplicity. If you can't measure the whole complex thing all at once, you break it down. Surveyors divide up an irregular area into a series of smaller, regular shapes like trapezoids that we do know how to measure easily. It's really the art of clever approximation.
Now this isn't just random guesswork. To make these approximations as accurate as humanly possible, surveyors have developed a couple of really key mathematical rules. You can think of them as two different tools for two slightly different jobs.
So check out the difference here. On the left, you've got the trapezoidal rule. It basically connects the dots with straight lines, making a bunch of trapezoids. It works, it's pretty good, but it can kind of miss the subtle reality of a curve. But Simpson's rule, on the right, is a little bit smarter. It assumes the boundary isn't a straight line, but a gentle curve, a parabola. This lets it hug the true shape of the land much, much more closely.
And this, right here, this is the crucial point. When you're dealing with the natural curving lines of the real world, accuracy is everything. And as the data shows time and time again, Simpson's rule is just flat out better. It gives you a more precise measurement simply because it respects the curves.
So, okay, we've figured out how to measure the area of a tricky plot of land. That's fantastic. But what happens when the project gets bigger? I mean, much, much bigger. What if you're not just measuring the land, but you're actually planning to move it? You know, to build a highway, or a dam, or a railway?
This is where we get into the wild world of earthworks. It's all about calculating exactly how much soil you need to cut from a hill and how much you need to fill a valley. And trust me, getting this right is the key to massive, and I mean massive, cost savings on these giant construction projects.
To manage this huge logistical puzzle, engineers have this amazing tool called a mass diagram. The best way to think about it is like a visual master plan for moving dirt. It tells contractors precisely where to dig, where to dump it, and the most economical way to get it from point A to point B, making sure no pile of dirt moves any farther than it absolutely has to.
Now, reading this diagram is actually way simpler than it looks. As you move along your route, if the line goes up, you're in a cut section. You're digging stuff out. If the line goes down, you're in a fill section. But here's the real magic. See that horizontal line? You draw that across a loop, and it connects 2 points where the amount of dirt you dug out perfectly equals the amount you need to fill a hole. It's a blueprint for perfect balance. But here's the thing. All of this beautiful, elegant planning, from Simpson's rule to the mass diagram, it's all built on a foundation of pure precision. You can't plan to move mountains if you can't measure them with incredible accuracy first. And for that, you need a very special instrument.
So, it's time to meet the hero of our story, the Theodolite. This instrument is the absolute cornerstone of modern surveying. It is a marvel of precision engineering that allows for measurements that are, frankly, almost unbelievably accurate.
Its job sounds simple, but it is incredibly difficult to execute. Measure angles, both horizontally and vertically, with the highest degree of precision you can imagine. Pretty much everything a surveyor does flows from this one fundamental capability.
And because of that, its applications are literally everywhere. I mean, from laying out the perfect angle for a property line, to making sure a road has the right grade for water to drain, to setting out those huge sweeping curves you see on highways and railroads, the Theodolite is the tool that turns a blueprint into reality out on the ground.
Okay, so we've scaled up from a field to a highway. Now it's time to take the final leap. How do you apply these same principles to create a super accurate map of an entire nation, a vast, complex landscape? You can't just go out and measure it piece by piece. You need a bigger, more elegant system.
The answer, believe it or not, lies in the simplest, most powerful shape in geometry, the triangle.
The method is called triangulation, and it's how the highest order of surveys, called geodetic surveys, establish rock-solid control points across enormous distances.
Now, here's the truly brilliant part. You don't have to measure every single line. No way. Instead, surveyors create this huge web of interconnected triangles. They go out and they meticulously, painstakingly measure the length of just one side in this whole network. That's called the baseline. Then, with a theodolite, they measure all the angles in all the triangles. And with just that information, they can use math to calculate the exact length of every single other side.
And the accuracy here is just staggering. It's hard to even wrap your head around it. In the highest level of triangulation, the sum of the angles in any triangle has to be 180 degrees, right? Well, the average error they allow, how much they can be off by, is less than 1 second of an arc. A second of an arc is 1/3600th of a single degree. It is an almost perfect measurement.
So it all comes together in this beautiful three-step dance of precision. Step 1, measure that one single baseline like your life depends on it. Step 2, use that trusty theodolite to measure every single angle in your network. And finally, step 3, let trigonometry do the heavy lifting to compute the lengths of all the other sides, creating this rigid, accurate framework that can span hundreds and hundreds of kilometers.
So just think about where we started this journey, with a simple, very practical problem. How to measure one funky-shaped plot of land. It was a puzzle that we solved by just breaking it down into smaller, manageable pieces.
And by scaling up that exact same core idea of using simple shapes and incredibly precise angle measurements, we arrive at a system that's powerful enough to map an entire nation. The whole thing, all built from this beautiful, interconnected chain of simple, powerful triangles.
It's the hidden geometry that underpins our entire modern world, from your backyard fence to national borders. So, the next time you're driving and you see a surveyor out on the side of the road peering through an instrument on a tripod, what hidden geometry will you see?